Hello, my name is Lucas, and I present Temporal-Scope Grammars, which are a method for generating polyphonic music. Automatic composition is very interesting as it allows us to make original music in real time without a human composer. Depending on the approach, the music can also adapt to parameters, which is useful for building interactive applications. Temporal scope grammars are based on formal grammars, which are a type of rule or constraint-based system. Compared to other methods, especially machine learning, grammars are very transparent and offer very direct control. The downside is that you need to provide domain knowledge yourself. You need to have a concrete idea how your music is structured. In that sense, it works very much like traditional programming with a domain-specific language. In prior works, grammars are often used for generating sequential structures. So the first problem we solved is how to generate music with overlapping notes and chords. The second challenge is to guarantee that notes that are close in time share metric and harmonic context. For example, if we have multiple parallel voices, all of them should use the same meter and harmonic progression. Let's start with the basics. What is a grammar and how does it relate to music? Well, grammars in natural languages define relationships between the words of a sentence. In music, instead of words, we can have a vocabulary of notes. And instead of a sentence, we can have a sequence of notes, which is a melody. As a musician, you might recognize the first notes in that melody as a G7 chord. We can add this G7 abstraction to our vocabulary and express the placeholder relationship between the chord and its notes with an arrow. The remaining notes form a C major chord. And finally, a G7 followed by a C major chord can be called a cadence. We have essentially built a parse tree for the melody and translated it into 3 replacement rules, one for each internal node. Now if we start at cadence and simply follow the replacement arrows, we get the melody as the output. So in general, a grammar is fully defined by a vocabulary, rules, and a starting point. Given a sequence of notes, we can play it in order like before, but each note has the same duration. To allow for rhythm, we can add another dimension to the elements of the vocabulary, which we call span. The span is a number that encodes the duration of a note. So now we can have varying durations and make a rhythm. But what we want is polyphony, where at any time multiple notes may be heard. In this example, the blue and yellow notes form 2 short melodies that play at the same time, but have slightly different rhythm, and the orange notes form a chord, which is 2 or more notes over the same time interval. Overlapping notes are essential for modeling many types of music, for example, if we want to have multiple instruments, or even just 2 hands on a piano. How can we represent this as a sentence of our grammar? Well, we could model music as a sequence of chords rather than a sequence of single notes. This is similar to music notation where there can be multiple note heads on a single stem. It allows us to intuitively represent melodies, chords, and rests, but we cannot express 2 rhythms at once like the 2 melodies from before. Another solution would be to have multiple monophonic sequences that are played at the same time. Here one can have different rhythms, but there is a global maximum on a number of parallel notes. If you need a chord at a point in the piece, you need at least as many voices as there are notes in the chord. The chord will further be fragmented across the voices, which can be a bit unintuitive. Yet another possibility would be to use multiple sequences of chords. This would come close to the structure of sheet music. While this would be powerful enough in theory, it adds a lot of global structure and implicit relationships between the notes, which means our rules would become more complex and less reusable. Instead, temporal scope grammars solve this problem with a more fundamental representation inspired by other music-related technologies, such as the MIDI format. We simply add a time parameter to each note, which encodes the absolute starting time. Notes are now completely independent from each other, each has an explicit time interval, and we can place them in sequence, in parallel, or in arbitrary arrangements. This time interval is what we mean by a temporal scope. We had this rule before, which replaces a cadence with a G7 and a C major chord. It doesn't really work anymore with the added dimensions, and users can define custom dimensions as well. The pseudocode shows how we would represent this rule in our system. It replaces a cadence over a time interval and generates two sequentially arranged chords, just like before. The new rule is more complicated, but is also a lot more powerful. On the left side of the arrow, we can use logical expressions, which allows us to select whole subsets of the vocabulary. For example, the rule will select any entity of type cadence, regardless of the time span or other parameters. On the right side of the arrow, we only specify what has changed. Everything else would just be inherited from the replaced object. For example, if we remove the time-related stuff, the chords will have the same time span as the cadence. And finally, we can calculate new values by using the values of the replaced object. This allows us to make relative changes, for example, move the note by a number of semitones or resize the time span. The rule is now very flexible as it generates the structure for every possible starting note and every conceivable time span. The only annoying part is the calculation of the new temporal scopes. Placing two chords in a sequence should after all not be so complicated. To aid the composer, our system provides a small set of operators for working with time spans. As we have seen, we can directly change the time parameter to move a note, or we can change the span parameter to resize a note. The split function can be used to distribute parts sequentially, allowing for arbitrary rhythmic divisions. It essentially computes the temporal offsets for you. The repeat operators can be used to repeat a time interval of a certain length until the original either overflows or is fully covered. Back at our rule from before, we can now remove the time-related calculations and replace them with a split operation from our library. Now it is much simpler, but still has the same behavior. The two remaining rules need to be upgraded as well. Here we use an additional chord function, which uses a loop to generate a certain number of chord notes. This should mainly just show that the system is extensible with new functional components, and over time users can build their own function library. The complete grammar with all three rules now generates this pattern. The grammar that we have seen only generates constant output. It will always be the same. We're still lacking variation, so here's a quick summary of the randomization features. We can define multiple rules that realize the same placeholder, and the algorithm simply picks one of them at random. We can define optional branches that are used with a certain probability, and we can use random choice or random sampling for calculating parameters. If you use these features plentifully in your grammar, the output will be very different every time you run the program. Using this combinatorial explosion is how the grammar is capable of generating new original music. With randomization, we have to consider the second challenge that I mentioned in the beginning. Consider this common situation. There are multiple parallel voices, for example, a melody and a bass line, and they should both be synchronized in some aspect, for example, to the same harmonic progression. Due to randomness, we cannot just generate the progression for each voice, as they might end up differently. Also, since our grammars are context-free, we are constrained to a tree-like data flow, and shared information must be provided via common ancestor in the tree. Our solution to this problem is again based on explicit time spans, in particular an operator that we call query. So first we would generate the chord progression and then store it in the common ancestor of the voices. Next we generate the voices so that both can inherit the same chords. And finally we use query to find a chord that overlaps with the current note. Again, this works because each note as well as each chord is associated with an absolute time span. We're essentially passing down a time-dependent function that we then sample when we need it. We implemented the system as a TypeScript library, and it comes with a web-based playback and visualization tool. So far, we have built 3 generators. The first generator makes short musical fragments, and I will demonstrate it in a video. The second generator extends the first generator with additional instruments and higher level structure. The third generator generates waltzes, complete with intro and outro. In prior works on grammars for music generation, polyphony was either not considered or limited in certain ways. We define a grammar system that is capable of polyphony on any level of the derivation tree and can be used to generate large and small scale musical structures. We can further synchronize voices using a timespan-based query mechanism. There's still a lot that can be improved. Using TypeScript as a frontend is not ideal because it is not very accessible for the average composer. As an alternative to random selection, we could integrate user input more directly into the derivation process. And we could extend a library, which is still quite small. The source code for the library is currently not public, but the generators and a number of examples can be found on GitHub. I hope you enjoyed this talk, and thank you for your attention.